Now, we've already established that an object in circular motion must be rotating, right? So let's consider a car. This is an aerial view. We're seeing a car. So here's my car. Yes, my car is a box, just like everything else, which is going counterclockwise. Okay? So at this point in the circle, you know that he's traveling in this direction. Okay? At some later point, he's going in this direction. Correct? Now, something had to change between here, between this one and that one, because he has changed direction. Therefore, he must have accelerated. Okay? So in order to do that, we need to find out what the change was. So I'm going to take the first vector right there, this one. Okay? So that's what he started at. Okay? Now, he's going to have some kind of change, which is then going to result in this vector, which needs to have the same length, but now it's in the other direction. So this is the resultant vector. Okay? So this is the resultant vector. That's what he's doing after his acceleration. And then the first vector is his starting. So what is the change? Well, you take the initial, and then you add the change. So this is the change in velocity, and that gives you the resultant vector. So that change is defined as our acceleration. And you'll notice that over the course of that change, that is always pointing towards the middle. This is the average acceleration. So from the middle, it's pointing towards the middle. You can do this from any two places on your circle, and you'll find that the acceleration always points to the middle. Here, look at this. Let's take this one over on the side. Let's go from here to there. All right? So we have going down, and then we're going to add something on, and then in the end, he needs to be going this way. Okay, so what is the vector that needs to be added to our initial vector? What's the change to end up getting that final vector? Well, it needs to go in this direction. And you'll notice, you'll notice that that vector between these two, the average acceleration, is that one right there, towards the middle. From this, we can start to recognize that in circular motion, the acceleration is always towards the middle. This is how an object can maintain its constant velocity. We also talked about this with respect to energy. This is important because the force must be towards the middle. That's the only way that that thing causing the circular or rotational motion will not be doing work and will not be adding energy into your system. All right? So there we then have the idea behind the force causing this motion, or the acceleration. Remember, force, I use force and acceleration interchangeably because we know that force equals mass times acceleration. So if the acceleration is towards the middle of the circle, the force must also be towards the middle of the circle. All right? So from this, we can do centripetal acceleration. All right? Now, I'm not going to go through a proof of this formula. If you want to go through a proof of this formula, you can find one. There's a fairly good one on page 251 to page 252 of the Cambridge-Sokos book. And they talk through a derivation of this formula. I don't think that the derivation of that is super duper important, nor do I really have time for it right now, as I'm trying unsuccessfully to keep the length of this video down. So therefore, we can now say, okay, well, I can calculate the acceleration if I know the speed. Now this, remember, this only works if the speed of the object is constant. If the speed of the object is not constant, it's going to require some stuff that we can't do right now because most of you haven't done calculus yet. So at this point, acceleration, we have to assume that the speed is constant so that it's actually going in a circle, not any type of ellipse or elliptoid or anything else weird. And then that you can see obviously that it's going in a circle because you would then have this constant radius here. Okay, so can we rewrite this acceleration in terms of the angular speed? Well, yes, because we know that our velocity is equal to the angular speed times the radius. So I can go ahead and put that in. So A equals omega r squared over radius, which gives us, when I work it out, I'll have omega squared r. Okay? Now, that's just another acceleration is again related to our angular speed. Okay? We can rewrite acceleration in terms of angular speed and velocity as well, if we really want to, right? Because we can calculate the velocity based off of the acceleration. So if I wanted to, I could say put this in. I could put, I know that omega, if v is equal omega r, omega is equal v over r. And so I could put v over r in for one of those omegas. And so then I would have omega times v over r times r, which would be omega v. So omega v would give me the acceleration. Now keep in mind, this is not angular acceleration, this is just the acceleration of the car going around the outside of the track. Now again, remember that the direction of the acceleration is always going to be towards the center of the circle, and that's going to be very important as we continue to go through. Alright, so let's look at another question. A ladybug is clinging to the rim of a spinning wheel, which is spinning counterclockwise very fast and is slowing down. At the moment shown, what is the approximate direction of the ladybug's acceleration? All right, so first off, okay, go ahead and pause, think through, take a minute or two, and let's answer it. Okay, so first we have to recognize that if the ladybug is going in a circle, if it's going in a circle, that there must be acceleration towards the middle. All right, so first we've got a component of acceleration towards the middle. Now, secondly, it says that it's slowing down. So it's going counterclockwise, so it's moving in this direction, which is not a force. It's not a part of acceleration, but that direction is moving. So if it's slowing down, it must have acceleration pushing it backwards in this direction. So if I take those two accelerations, one towards the middle and one slowing down, then the resultant vector is this right here. Okay, so that is the acceleration. Let's see, acceleration that way. And so it's got to be something such that it matches that. Well, it's obviously not straight down, so let's take that one out. It can't be this one that's completely going the wrong direction. So the question is it directly to the left or is it down? And I'm going to just make a guess that it's going to be B. All right? Now, if you said C, that's also okay. It actually probably depends a little bit on how much he's slowing down. I realized that I probably should have put the bug right on the side here. If I'd put the bug right on the side, then it would have very clearly been acceleration towards the middle, a little bit of deceleration. It would have had to have been C. So based off of where it is, I apologize. Go ahead, give yourself credit if you said either B or C, based off of the position of where the ladybug is now. All right, let's try another one. Pause the video, answer it, and then play. All right, so here's my take on it. I see that he's going at constant speed. So the same speed here as the same speed here. What's the difference between those two? Well, this is a circle with a large radius. This is a part of a circle with a small radius. So if I think about acceleration, because the question is when is the acceleration the largest, a equals v squared over r, correct? So if a is v squared over r and v is the same for both of them, this part's staying the same, so whichever one has the smaller radius is going to end up with a higher acceleration. So the smaller radius would be this position here from 3 to 4, okay? And so that's going to be my answer, is from 3 to 4, which would be letter B. Okay, larger acceleration. Now this should make sense if you're thinking of trying to go around a tight corner or taking a wide turn around a corner. Which one's harder? Which one requires more force from you or more work by gravity? Well, a tight corner is much harder to do. right? It's much more likely that you're going to slide because friction can't hold you. Friction's actually helping you here. I know we're often hard on friction, but friction is the reason we can do everything we can do. Without friction, we wouldn't be able to walk, we wouldn't be able to turn. Turning wouldn't matter because you can't walk. So, I mean, none of those things would be possible if we didn't have friction, which was pushing us forward or pushing against us as we push on the ground. So anyway, that'll be important to another slide coming up here in a second. So higher acceleration because of higher force, all because of that smaller circumference there, that smaller radius. It's not smaller circumference, smaller radius. All right? Next question. You've seen this, right? You've seen this ride. If not, go watch a video of it. It's pretty hilarious. People are in there. It spins around really fast. It goes zoo, 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 and it goes around in circles as fast as it humanly can, or not humanly, as fast as they can get it to go. And the people feel like they're being pushed up against the wall. In fact, at some point, the floor drops out from under them, and you can see that here. They were against the wall. The floor has actually dropped out, and yet they don't fall. They are against the wall. The force between them and the wall is strong enough that they are not sliding down the wall. Okay? And so you can hang around. I did this once, and we were able to go upside down. We were able to turn ourselves upside down and all sorts of crazy things before it started slowing down, and we had to flip ourselves right side up so that we didn't fall on our heads when it stopped rotating. Now, very often, people refer to this as something called centrifugal motion. Okay? Centrifugal. Actually, I don't even know how you spell it. The reason I don't know how you spell it is because there is no such thing as centrifugal motion, right? What people want to say is that they are being thrown against the wall of this amazing ride, and there's some magical force that is pushing them back into the wall, holding them against the wall so that when the floor drops out that they do not fall. That makes absolutely no sense at all. What in the world is pushing them against the wall? Nothing. There is no centrifugal force. Okay? What is happening is when you're going around that circle,